Last time we started section 5.1, we were talking about addition and subtraction of integers. We looked at some models for addition and subtraction with chips, with number lines, with charged fields, and with patterns. And we also looked at some absolute value comments and how that works a little bit. And we're going to take a look today at properties of integers and then continue on from there. So we have seen most of these properties before. And most of these properties get just expanded once we get to the integer system. So our first property is the closure property of addition of integers. So the closure property, do you remember what closure property said? Yeah, as long as A and B are in the set to begin with, given integers, they're integers right here, A, B, and C, then A plus B is an integer. And we have this thing that says is a unique integer. In other words, if I had all of my integers dancing in the room, like the whole numbers were in my book, right? And all the letters and so forth, right? But if I added two of the integers together, I would get another integer. Any two integers added together give me another integer. What is commutative? What does that mean? Yeah, you can switch the order of the addition. So A plus B is equal to B plus A. Okay? So it's the same as the whole number property. What does associative look like? Okay, so if I start with the parentheses like this, Leah, can you tell me what I would write down next?
Is it A plus C plus B, or is it A plus B?
The second one.
Okay.
You do the A plus B, so you don't change the order up any. You just change the location of the parentheses. So A, B, C is still in the same order, A, B, C.
How would commutative work for integers if you have negative numbers?
You just have to keep the sign with the number. So like if you had 5 plus -2, then you'd have -2 plus 5. Yeah, you just keep the signs with the numbers. And there's actually an example question about that a little bit in your homework today, or maybe it's the group work, one of the two.
But it's because we're doing addition, not subtraction.
Right.
Subtraction.
Yeah, subtraction's still got issues. How about the identity property of addition? Yeah, so we have this number 0, and 0 is the identity, or the identity element, sometimes it's called. Okay, I don't think I have enough, maybe I have barely enough space. There's identity. And you're right, if I have A plus 0, or 0 plus A, either order of that equals A. So I have the same additive identity that I had before. None of that's any different. We get a new identity, though, that we did not have before. Not identity, excuse me. We get a new property that we didn't have before. This is the inverse property, right? For every integer A, there exists a unique integer -A. It's called the additive inverse, such that A plus -A, or -A plus A, is equal to the identity 0. Why did we not have this before? We didn't have negative numbers before.
It's like native or reciprocal, right?
Reciprocal is for division, and that's we give fractions. So when we do rational numbers, like in proportional and statistical reasoning, we have that additional property, but we don't have that here yet. Yeah, with integers, though, we get the additive identity, the opposite. I didn't mean identity. Additive inverse, the opposite of the number we had before. Now, it's important to notice that it says for every integer A. So if I have a positive integer, then its inverse is going to be a negative integer, right? What if I have a negative integer?
It's going to be positive.
It's going to be positive. And are there any other types of integers that are neither positive nor negative?
0.
0. So what would be the additive inverse of 0? 0. He's his own inverse, right? 0 plus 0 equals 0. So he does have an identity or an inverse, it's just himself. Okay? All right, a couple more properties. If you have the opposite of a negative number, it's a positive number. Right? So the opposite of -A is positive A. Okay? If you've ever seen the movie Stand and Deliver, they chant this. They go, a negative times a negative equals a positive. Right? And the issue is the same issue here. We're not talking about it in terms of multiplication. We will in section 5.2. But here we're talking about it as the opposite of a negative. So an opposite of a negative is a positive.
So like, sorry, I have a lot of questions.
It's okay.
Like I remember when I was in like elementary school, one of my teachers, like this kind of translates into, this might be something different, but like when you're actually doing a problem, like if you have, I can't remember, like, okay, if you have like 2 minus a negative 3, it's like 2 plus a positive 3. Right?
Correct.
Okay.
Yes, and that's one of the mnemonic devices to help students remember as well. So you're thinking about a problem that would look something like 5, minus negative 2. And that would turn into, like you said, 5 plus 2. And the reason is because the opposite of subtracting 2 would be adding 2.
Like our teachers should have us write like plus a positive. So
Yep,
we
and you
would see
can.
it.
Yeah, and a lot of teachers, especially when they're first teaching them, will. So you keep the first number. This is what Leah was saying. So you keep the 5, and then you change the negative, and you change the sign on the inside as well. Whatever it was before, now it's opposite. Yeah. All right, if you have two numbers that are the same, A equals B, then it will be the same, they will equal each other if you add a number to them. So A plus C is going to equal to B plus C. And it feels like a silly thing. I mean, obviously, if 5 equals 5, then 5 plus 2 equals 5 plus 2. And I get that. And for whole numbers and for integers, that sort of seems a little bit silly. But this fact right here is a super useful fact when it comes to solving equations, right? If you have two things that are equal on the two sides of the equation and you add something to both of them, the balance stays the same. And then the last one says that if you have a negative A plus a negative B, then this equals the negative of A plus B. Okay, so we can think about it, at least we can, because we've gotten beyond what this is in mathematics before, as factoring out the negative. You can also think about it and we'll do some models of this actually in a minute, as moving, again, if you're already at negative A, that is the left-hand side of the number line, you're moving further left. So you're adding additional negative value to what you've got. And this will lead into my examples here in a second. We have two more. Integer subtraction is next. For any integers A, B, A and B, I should say that, A minus B is the unique integer n, such that A equals B plus n. This is the same definition for integer subtraction that we had with whole numbers. The only condition is that we don't really have to have, the only condition we don't have to have is that before we had A had to be bigger than B to do this, because otherwise we wouldn't have had whole numbers. So we don't need that now because we have negatives. So this is saying that if I had A minus B and it equals n, this is the same thing as saying A equals B plus n. And if you think of it from an equation standpoint, you can, sort of undo the minus B by adding B to both sides. If you think about it from a subtraction standpoint as well, you can ask yourselves A minus B, what is going on here? Well, this is A equals to B plus some other number, right? That's what subtraction is. It's how much is missing from one piece to give you back the other piece. And our last theorem is theorem 5.4, or 5-4. And it says that A minus B is the same thing as A plus a negative B. And the mnemonic device that Leah mentioned works for this as well. If you keep the first value A, and then you change the negative to a positive, and then you change the B that is positive to a negative, that's your keep, change, change that would work for this too. And we'll look at this again from a modeled standpoint in a minute. I think that helps more than anything. All right, you guys ready to look at some models? You're going to see these models, and you're going to be like, I've already seen these models before. But we're doing it for subtraction now. So the first model is called the chip model. Do you remember our chip model? Excellent. I'm so glad. All right, when we did the chip model, what we did is we drew a circle. And inside of our circle, we had different chips that represented different values. And we had what colors for what? If you have colors with you, you can use differently. But what did I use? Do you remember? Yeah, we used black for positive values. And we used red for negative values. All right, so if we're looking at this, we're going to start with the 5 at the beginning. And the 5 at the beginning says that I have 5 black chips, right? Because that's the sign on it. So I need to put in 5 black chips. This symbol right here, so I don't want us to use the mnemonic device keep, change, change, because I want to show you from a practical, like concrete model standpoint why keep, change works, okay? So don't think I'm going to change these both signs to negative. That's not the point. My point in showing you this is to show you why that process actually makes sense, okay? So this subtraction sign means what? Take away or remove something. And I'm supposed to remove what according to this right here? -3, which would be 3 red chips, right? I don't have 3 red chips to remove, do I? How am I going to remove 3 red chips if I don't have 3 red chips to remove? Well, somehow I got to have 3 red chips in there, correct? So consider doing this. Did I really add anything to my system inside of the circle? No, I added in what's called a 0 pair. So for those of you who have done proportional statistical reasoning with me, we did this with algebra tiles, okay, with the manipulatives at the end. You added in the number 0. Now I have 1 red chip, but how many red chips did I really need? 3. So I can go through this same process 3 times, and the number that's inside of my circle is still the number 5. Does everybody agree with me that 5 is the number inside my circle? Yeah. Those 3 pairs of things I added at the end, those are 0 each. But now I actually have the 3 red chips that I can, in fact, remove. So now these 3 red chips can be removed. And when I remove my 3 red chips, what will I be left with?
8 black.
I'll be left with 8 black chips. And this would then be the answer, 8. And now you have a concrete justification for why it would make sense that a subtraction of a negative equals positive. Right? 0 pairs. We're going to try that 0 pairs model again. We're going to do it with charged fields. Of course, just like before, it works the same way. We don't need to worry about colors on this model. But I started out with 5 positives. Do you remember that? And this step right here says that I'm supposed to remove what? 3 negatives. And I don't have any negative switch to remove, so I have to add them in 0 pairs. So what am I going to add? Yeah, I'm going to add a positive, negative 3 times. So 3 pairs of positive negatives. And once I do that, I can remove the 3 negatives, which leaves me with what? 8 positives. Okay, so again, are you going to do this every single time you need to add and subtract positive and negative numbers? Of course not. That's not the point. But the point is to give kids some sort of sense of why in the world we've got this magical thing that says I can keep, change. Right? Why in the world I can change minus a negative into a positive? Because that sounds a little funky. I will tell you, I have a brother-in-law who at the time when he contacted me, I was already working here. So, and he's 2 years older than I was. So he would have been already in his 30s and he was finishing up a degree. I don't know if I was here actually or not, but he was definitely in his 30s when he contacted me about this. And this whole idea of subtracting a negative and getting a positive just went like this. And the man's in his 30s. Okay, and we went through several different models of why this would have to work, why it has to make sense. We talked about number lines. We talked about chips. We talked about this. We talked about that. And I don't know if it ever really did click, going to be honest with you. But this is something that people really struggle with, this idea. And just knowing a rule is not always enough for a lot of people. For some people, they're like, fine, I know a rule, I can move on. But not everyone's like that. So we'll do the number line model now. So the number line model is very difficult to draw in a way that makes any lick of sense. But kinesthetically, we can do it in a way that does. Okay? So I'm going to draw the picture. And then we're going to talk about it. We're going to start with 5. And in a minute here, we're going to move from the 5 we're at forward 3. But I want to show you, this is all I can do in terms of my picture. This is the picture, which doesn't really lend itself to a lot of explanation. But let me actually do it with the desks in front of you, and you can think about what would happen with your children if they were doing this on a number line in the classroom, okay? Are you ready? Okay, so we're starting here, and we're going to move forward 5. 1, 2, 3, 4, and 5. The first negative means that I'm going to turn around. What do you think the second negative means I'm going to do?
You're gonna turn back around.
Well, I could. But the way that your book presents it is I'm going to walk backwards. Right? I'm going to walk backwards 3. So if I walk backwards 3, because I'm walking backwards 3 and after I turned around, I'm actually then at 8. Okay? You could think of it as turning around twice. That's okay too. We can do it that way. Your book talks about it from the other perspective, but I think both work just fine.
Wait, so turning
But you can't draw this, right? I mean,
turning around counts as one?
well, so what Amy is suggesting is that if I were walking 5 in this direction, sort of going towards this direction, the first negative means I turn around, and the second negative means I turn around again. So there are 280-degree turns, was her idea, which works. And then you'd be forward 3 again, because the next number's 3. Okay? Either one.
Why would it be 3 like on the drawing? Just because you're going 3 more?
Yeah, it's 3 steps. So the drawing part of it is less helpful.
Yeah.
But kinesthetically, like moving along a number line in a classroom, it really does help a lot, this idea of turning things around. All right, the last model is a pattern model. And so we're going to take a look at this one. Again, we did this last time with patterns, and I showed you how to think about it. So you start with something that you know how to subtract. 5 minus 2 we're all good with. And the children in your classroom who are probably going to be in 6th or 7th grade are certainly good with this. They've been doing it since 1st or kindergarten probably. Okay, so 5 minus 2, and then you have 5 minus 1 and 5 minus 0. All of those are whole number subtractions that we like just fine. And we get 3, 4, 5. Okay, so continuing the pattern, again, the whole point of this is to justify why keep, change works. So if we continue the pattern to 5 minus a negative 3, we notice that on the right-hand side, the part I haven't filled in yet, what's happening to the numbers as I go down the right-hand side? They're going up by 1. So I went from 3 to 4 to 5. So then I'll do 6, 7, and 8. And if you compare the numbers, how do you get 5 and 3 to become 8? You add them together. And so again, from a pattern perspective, that justifies for us why minus the negative 3 must be a plus 3 from a pattern's perspective. Okay? Our goal in thinking about these models is justification for why it works, why the mnemonic devices work. Okay, a couple other things for you to take a look at, and then we'll be done in this section. PEMDAS. You guys heard of PEMDAS before? Do you have an acronym that you know and you love that you've used? Yeah, that's usually the one that people have heard. Please excuse my dear Aunt Sally. And what I'd like to suggest is that it's not exactly accurate, because I could call this PEDSMA. PEDSMA. I think I said it right. Okay, so here's the deal. Let's just go through each of these and remind ourselves what they are. What is a P for? That is parentheses. And what it means, and you should write this down, is it means that the things that are inside of the parentheses should be done first. Okay, it doesn't mean remove the parentheses. It doesn't mean deal with the parentheses. It means simplify what's inside of it. That's really what the P means. What's E for?
Exponents.
Exponents. Very good. So first we simplify what's inside the parentheses. Then if we have any exponents, we deal with the exponents. We square things, we cube things, whatever. These are just nice to put as MD, but they don't need to be MD. They could be DM just fine. Okay? MD, DM, this is commutative. Okay? Doesn't matter. PEDMAS. Okay? So you know what M and D stand for, though. What does M stand for? Multiplication. In fact, I'm going to write it this way. Multiplication. And the D stands for, of course, division. We've got multiplication and division. But really, what you need to remember here is that you move from left to right. So if the division comes before the multiplication, then you divide before you multiply. And the reason that this is true is because multiplication and division are really the same thing. Somebody lied to you somewhere along the way and told you they were different, but they're not. They're the same thing. Okay, in terms of order of operations anyway. Same thing. AS. Again, we could have just as easily have done this operation and called it SA. There's nothing special about the A and then the S. Yeah, we could end up with a SA at the end, right? A, of course, is addition. And S is subtraction. And again, it's important that you're moving from left to right. So if the subtraction is before the addition, you're going to subtract before you add. You're moving from left to right. All right, and I think we have one example with order of operations to finish our, oh look, this is one I didn't get erased. Pretend like you didn't see it. Just like that, it went away. It's like a miracle. It's a miracle of technology right there. Just disappear things. All right, simplify the following using order of operations. So the first thing we look for are parentheses and we say, there aren't any. Then we look for exponents and we say, there aren't any. And really, most of the problems you deal with aren't going to have a lot of that at this age level, right? They're not going to have a lot of it. But as you're taking a look, then we look at multiplication and division next, and we move from left to right. And what's the first multiplication or division you see?
6 divided by 2.
The 6 divided by 2. So I'm going to be very explicit and do these sort of step by step. You don't have to be this explicit on your paper, but I want to make sure everybody sees the steps as I do them. So the first thing we did is 6 divided by 2. Then what do we do? We multiply the 3 times the 4. So 3 times 4 would be 12. Fabulous.
Oh, I should leave this 6 divided by 2. Oh, sorry.
Yeah,
Sorry.
this piece got replaced with the 3. It's okay.
I didn't do it.
It's all good. So now I've got 5 minus 2 plus 12. What's the next thing I do? 5 minus 2, which is 3. And then I do the 3 plus 12, which is 15. Now in your book, the questions they ask phrase things a lot like this. What is the last operation that you'll do in this problem? And the last operation you would do was to add 12. Are you guys with me? That's how they're going to phrase that. So if you want to write down 3 plus 12, that's fine. If you just want to write down add 12, that's fine. But that's how they're going to phrase this, because the last operation should be the same if you're doing the order of operations properly left to right with the order, PEMDAS.